That table of standard reduction potential that I just showed is actually quite useful, but one of the uses is, of course, to help us calculate the cell potential of any pairing of redox partners, right? So if I know that I want to make a battery out of, let's say, aluminum and iron, for example. Would that work or not? Well, I can just calculate the E cell. As long as the E cell is positive, that tells me that that battery would work. And that would also tell me which element should be placed as the cathode and which element should be placed as the anode. Another important use of that values that we just saw in that table is to figure out relative redox strengths, which just means that figuring out who's going to be a stronger oxidizing agent and who's going to be a stronger reducing agent. And the idea of this goes back to an analogy again with that acid-base reaction that I mentioned to you before, which is that if we have Ka, the acid ionization constant for two different acids, we can immediately know which acid is stronger. And once we know that, we can also immediately know which conjugate base is going to be stronger and which conjugate base is going to be weaker. The same idea here. If we have two elements, in this case, two ions, right? For example, X plus and Y plus. If we know that X plus has a larger reduction potential than Y plus, that means that X plus can reduce more easily than Y plus, which means that X plus can better accept electron than Y plus. So that means the other side of it, which is, if you will, again, the conjugate species, although we don't call it the conjugate species, which is the Y and the X elements, that means that Y is going to be a better electron donor than X, okay? So you might want to work this out with a reaction. We've done it a few times here, so I don't want to do it again here, but you might want to write it out for yourself to convince yourself that that is the case. Alternatively, if P compared to Q here has a larger oxidation potential, again, what that means is P is better at donating electron than Q. So therefore, the opposite species, the ion species, the P plus and the Q plus, in this case, the Q plus is going to be a better electron acceptor than P plus, okay? So let's take a look back to the three species that we've been looking at again and again and again. We know the three reactions here. They're all reduction reaction. You can see that, right? Copper, potential, and then the zinc. Okay. And so how do we determine who's a stronger oxidizing agent, who's the stronger reducing agent? Remember, we want in the end a positive cell potential. So that means the more positive this number is, the more likely that process is to happen. Or when I look at something like this, what I can say is that copper 2 plus is more likely to be reduced compared to H plus, which is more likely to be reduced compared to zinc 2 plus. Just by looking at the values right here and ranking of those values. Okay, so if I say something is more likely to be reduced, that means another way of saying that is copper 2 plus is a stronger oxidizing agent, right? Because it's more likely to be reduced compared to H plus, which is a stronger one compared to zinc 2 plus, okay? So that's how you can derive some conclusions out of those numbers. Now, what happens if we look at these guys here, which is the part that is oxidized? Well, then everything is flipped, right? So now I can say that zinc is a stronger reducing agent because it's more likely to be oxidized compared to H2, which is a stronger one compared to stronger reducing agent compared to copper, okay? So keep in mind what we're comparing every time. Sometimes we're comparing the ion form, sometimes we're comparing the element form. It depends on what reaction you're thinking about. Are you thinking about reduction or are you thinking about oxidation? Okay, so we just look at how we can determine the strength of oxidizing and reducing agent by relying on that value of half cell potential, right, which is in that table that I was showing you in the previous section. Now, we want to kind of put everything together, which is a topic that I've mentioned a couple of times so far, which is how do I predict what kind of combination of redox partners will give me a functioning voltaic cell? Now, the key information that you need to keep in mind here is that the value of the E cell has to be positive when the cell is working, meaning that there's a spontaneous flow of electrons from one side to the other. And of course, that means that the sum of the oxidation and reduction potential values have to be positive. Okay, that's one way to calculate it. The other way to calculate it is you assign one of the electrode to be cathode and the other electrode to be anode. And if you subtract those two numbers, it should give you a positive number as well. If it doesn't, that means the pairing doesn't work. If it gives you a positive number, that means the pairing works. Okay, now I want to do this in a context of an example. a lot of the points I mentioned here is really something I've mentioned in the prior videos as well. So I want to just jump into this example right here. So here you're given three different reduction reaction. I know these are reduction reaction because look, the electrons are all on the reactant side, right? So these are then all my reduction potential values, okay? Just the same as the one that you saw in that table from the University of Rhode Island. Now, what I want to know here is the following. Which ones will work if I were to pair them up together, right? How would I pair them up together? Who should be the anode? Who should be the cathode? And then the last question that this example is asking is rank the relative strength of the oxidizing and reducing agent. Okay, so what I want to do is just show you an example of how to think through one of these ones, and then you should be able to do the other two. So if I have these numbers right here, let me take a look at 1 and 2 first, okay? So I know they're both currently written as reduction values, right? So if I want to partner up, how should I do it? Well, here's some important points to keep in mind, okay? I show you on the right side here. Remember that when you pair them up, one of them has to be oxidation, the other one has to be reduction. You can't have both reductions, you can't have both oxidations. Okay, so that's one thing. If you're gonna make one of them oxidation, the other one reduction, that means you have to flip one of the reaction. Keep in mind that the values that you're given are always given as reduction reaction, which means one of the numbers needs to be flipped in the sense that the oxidation potential is always the negative of the reduction potential value, okay? Last point to keep in mind, the sum of the oxidation and reduction potential has to be positive. Otherwise, the voltaic cell will not function. Okay, so let's take a look back at the first two. We see that the first reaction has a positive 0.96 volts. The second one has a negative. Okay, so if the first one already has positive, remember, we want positive in the sum. So we want to keep that as reduction. And then the second one is negative, so that means we want to flip that. So we want to make the first one reduction and the second one the oxidation. Okay, so hopefully that makes sense, because when you flip that reaction, and let me show you how I write it here, you can see that this is the first reaction. I just keep it as is, and I wrote the reduction potential, which is positive 0.96 volts. The second reaction now, I flip it. I flip it so that it becomes N2H5 plus goes to N2N5H plus 4 electron. You see that now it's oxidation because now the electron is on the product side. The E oxidation is the negative of the E reduction. Like, look, the E reduction is negative 0.23, so the E oxidation is just positive 0.23. And that's what I have here, okay? And so then what I want to do is add these two reactions together to get my E cell. If you actually want to balance this equation out, you notice that the number of electrons are not equal to each other. So I'm going to have to multiply the top reaction by 4 and the bottom reaction by 3. Why did I choose those numbers? Because look, I need to balance out the electrons. So if you think back to how we balance redox equations, we always have to equalize the number of electrons. That's what I'm doing. Once I do that and I cancel out all the H pluses on both sides, then this is the balance equation that I get. And the E cell, here's the part that's really important. When I multiply those equations by the electron, I do not do anything with the E cell. The E cell remains unmultiplied. So the E cell for the actual cell would just be the sum of those two numbers that I found, 0.96 plus 0.23 volts, which is 1.19 volts. Okay, so again, the E cell value is not multiplied when you balance an equation, okay? Comparing to that analogy with water, what you're doing here is you're just measuring the height of the water. So if you have more water, the difference in height is still the same. It's not going to change, right? You can have just a bigger container where the difference in the level of water is still the same, okay? But there's just more water in here. So the height difference is not affected. The energy is affected later on. And so you'll see in the next video, we will talk about how to calculate energy out of this. Right now, what we're calculating is just voltages. So the voltage is not affected by the multiplication or the quantity of material you're using. The energy would be affected, okay? So that's how we would do that problem. What I just showed you is that first one right there, which gives you 1.19 volts. You should be able to come up with these other two pairing. Now, the other question that we need to address here is the relative strengths of the oxidizing and the reducing agent. So again, looking at these three numbers, we have this being the most positive, this is the second, and that one is the least positive. In fact, it's a negative number in this case. Okay, so what does this reduction potential tell us? Reduction potential tells us the ability of these species to accept electron. When they're accepting electron, they're getting reduced, which means they're oxidizing agents. So we're talking about how good these guys are being oxidizing agent. So the one that has the most positive value will be the strongest oxidizing agent. The one that has the least positive value will be the weakest oxidizing agent. So this is the strongest oxidizing agent, that's the second, and that's the third, okay? And that's what you see here in terms of oxidizing agents, strongest, middle, and weakest. Now, in terms of reducing agents, we would now look at the other side, which is these three species right here. And the order is exactly flipped. So the guy that is the weakest oxidizing agent now becomes the strongest reducing agent. Okay, so listen to what I'm saying. Earlier we're comparing oxidizing agent, now we're comparing reducing agent. So this guy is the strongest reducing agent, followed by this one, still in the middle, and then that one would be the weakest reducing agent. So you can see that's the pattern that I have here. But notice again that here I have different species compared to that one right there. So it's always the species is different, the process is also different, okay? I want you to also think about this particular question right here. You have a new battery system that you're trying to create from zinc and chlorine. The question is, what's the E cell of this? So what you need to do here is you need to look at the zinc going to zinc 2 plus, okay? So you need to find what the zinc going to zinc 2 plus reaction is in terms of its half cell potential. And then you need to look at chlorine going to chloride and what that half cell potential is. So this one is your oxidation, this is your reduction. Now, if you look it up on the table that I showed you before on that University of Rhode Island link, you should find that the oxidation for zinc is 0.76 volts. The reduction is negative 0.76 volt, but when you flip it to become oxidation, it's positive 0.76 volt. The reduction potential for chlorine going to chloride is actually given in that table, and it's positive 1.358 volts. So when you add these two numbers together, you should get a number that's about 2.1 volts, which is what this answer is.